Hi guys, welcome back. Audrey here. We're going to jump right back into partial fractions. And so when we do that, we're going to try to remember the steps of partial fractions and how we solve for those numerators. And also, while we're at it, we're going to learn how to do one of my very favorite types of integrals. So the first step of partial fractions is to divide if necessary. So in this case, I can easily see that the degree of the denominator here, the numerator, the degree of the numerator is equal to 2, and the degree of the denominator is equal to 3. So with the denominator, we have this factored, so we need to check, and that x times x squared gives me x cubed. We'd have to say, what is the highest power when we multiply them together? So that would be x cubed. My degree is equal to 3. So in our first step, we really have no division necessary. Necessary. So then our second step here, we want to factor the denominator. We can see that it's already at least partially factored, but we have that x squared plus 2x plus 9. So our question is, does that factor more? So does x squared plus 2x plus 9 factor more? And to answer this question, we can actually remember the quadratic formula. So the quadratic formula is the opposite of b plus or minus the square root of b squared minus 4ac over 2a. And this b squared minus 4ac here is what's called the determinant. We notice that it shows up in the quadratic formula under a square root. So if that value is negative, then that's going to give us a negative number under a square root, which doesn't work. So if we end up with a negative number under that square root, what that means is that this doesn't factor anymore. So if b squared minus 4ac is less than 0, doesn't factor. So let's check that here. Our b is 2, so we have 2 squared minus 4 times 1 times 9, which equals to 4 minus 36, which is minus 32, which is clearly less than 0. So x squared plus 2x plus 9 is irreducible. It doesn't factor anymore. Is irreducible. So here we can just say already factored. Now, whether or not a polynomial factors actually changes problems quite a bit. Being able to factor polynomials often makes the problem much easier. And a little bit later, we're going to see that via some problems that look almost exactly the same, but that have a polynomial that factors versus that doesn't. So it really is important to always check here, does your polynomial factor more? Okay, so that said, already factored, this brings us to our step 3, where we want to create our partial fractions decomposition. So we want to say negative 3x squared minus 2x minus 31 over x plus 1 times x squared plus 2x plus 9 is equal to, so we want our partial fractions decomposition here. We can see that this has a linear factor and a quadratic factor. Neither of them occurs multiple times, so they both occur only one time. So this puts us in case 3, and case 3 is when the denominator contains irreducible quadratic factors that are distinct, meaning they only occur one time. And so in this case, we have our x plus 1 as a denominator, and we have our x squared plus 2x plus 9 as a denominator. And we know that the numerators have to just be 1 degree less. So that means I'm going to have a constant on top of my ax plus 1. But on top of x squared plus 2x plus 9, I'm going to have a linear polynomial. So I'll have a bx plus c. All right, now step 4. So we want to solve for those numerators. So I'm going to start off by multiplying both sides by x plus 1 times x squared plus 2x plus 9. That's the original denominator. On the left side, I'll just have the numerator left over. With a, the x plus 1's cancel out, and it's multiplied by x squared plus 2x plus 9. And with bx plus c, The x squared plus 2x plus 9 cancels out, and I just have an x plus 1 left over. So we're going to solve this just using method 1. It's pretty straightforward to use method 1 for this question. We'll actually see the elusive method 2 in the next problem that we do. Okay, so method 1 says to plug in x values starting with your zeros of the denominator. Well, my denominator only has 1 0. That's x plus 1 equals 0, so that's x equals to negative 1. So we're going to plug in x is equal to negative 1. And here I'm going to get negative 3 times negative 1 squared is positive 1, minus 2 times negative 1, minus 31 is equal to a times 1 plus 2, I'm sorry, minus 2, my bad, 1 minus 2 plus 9 plus 0, because bx plus c is being multiplied by negative 1 plus 1, so that all just kind of goes away, it becomes 0. So here I have negative 3 plus 2 minus 31 is equal to a times 8. So 8a is equal to negative 32, which gives me that a is equal to negative 4. All right, so I plugged in my 1, 0, and now I still have 2 values left to solve for. What that means is I'm going to have to plug in 2 different zeros. So I'm going to start off by plugging in 0. That's an intelligent choice. I haven't plugged it in yet. It's super easy to plug in. So we'll plug in x is equal to 0. And when I do, I get 0 plus 0 minus 31 is equal to a, which is negative 4, 0 plus 0 plus 9, so negative 4 plus 9, plus b times 0, so this is just c here, times 0 plus 1. And notice plugging in that 0 was a really, really smart choice here because it eliminated b as well, which means that I'm going to be immediately able to solve for c, and I won't have to do a system of equations like we saw in the last problem that we did right before March 5th. So this negative 4, remember, that's my a. So here I get negative 31 is equal to negative 36 plus c, and c is equal to 5. Now we want to plug in another value. A good value to plug in that we haven't plugged in yet would be 1, because it's super easy to plug in 1s. So I'm going to go ahead and do that. That said, remember, you're welcome to plug in whatever values you want. So I have negative 3 minus 2 minus 31 is equal to a, which is negative 4, 1 plus 2 plus 9, plus b plus c, but c is 5, so b plus 5 times 2. So this gives me negative 36 is equal to 12 times 4, that's negative 48, plus 2b plus 10. So 2b is equal to negative 36 plus 48 minus 10. So 2b is equal to 2, which gives me that b is equal to 1. Okay, so we have a is negative 4, c is 5, b is 1. Now we can move on to step 5, and guys, it gets about to get really fun. I hope that you think so too. So we are going to rewrite our integral. We end up with the integral of a over x plus 1 plus bx plus c, so that's x plus 5 over x squared plus 2x plus 9. So this is negative 4 over x plus 1 dx, that's a simple integral, plus the integral of x plus 5 over x squared plus 2x plus 9 dx. Now this integral right here is an integral that actually shows up quite a bit at the end of partial fractions, because if ever you have that irreducible quadratic polynomial, this is almost always going to show up. So we want to think about how to approach this problem. We actually have a very special way of doing this precise integral. So we're going to put this as a star, and we're going to go down here and do it. So we have x plus 5 over the square root, I'm sorry, no square root, over just x squared plus 2x plus 9 dx. And we know that when we see something like this, when we see any problem, we're like, there's no simplification I can do. We eliminated that possibility. So then we ask ourselves if there's an obvious substitution. So I'm going to write down what that obvious substitution would be if it were there. So u is equal to x squared plus 2x plus 9. And du would be 2x plus 2 dx. Okay, so that substitution obviously doesn't work. I have an x plus 5 on top, not an x plus 2. And it's not like I can just multiply by 2 and then have 2x plus 2. If I multiply by 2, I'll have 2x plus 10 on the top. That said, we're going to do that anyway. So what I like to call this method is forcing a substitution. So this is a lot like special division, where we make the numerator look like the denominator. But in this case, instead of making the numerator look like the denominator, we're going to make the numerator look like the derivative of the denominator. We're going to force that substitution. So I'm going to start by multiplying by 2. So I'm multiplying the whole numerator by 2 and then dividing by 2. So I'll end up with 1/2 2x plus 10 over x squared plus 2x plus 9 dx. So I multiplied and divided by 2 to have that 2x, and now I want a plus 2. So I'm just going to put it there, plus 2. But like with special division, I also have to subtract it. So I'll have 2x plus 2 plus 10 minus 2 over x squared plus 2x plus 9, which results in 2x plus 2 over x squared plus 2x plus 9 plus 10 minus 2 over x squared plus 2x plus 9. And so now I want you to notice that this part right here has turned into something where the substitution works. So we're going to call this smiley face here. And we're going to go down and we're going to use that substitution on smiley face. So in other words, if I apply that substitution, I'm going to ignore the 1/2 out front for a moment because it's applying to both of those integrals. What I'm going to end up with down here is the integral, that 2x plus 2 is on top, 1 over u du, which is just equal to natural log of u plus c, which is natural log of x squared plus 2x plus 9 plus c. Okay, so we just finished smiley face. Now let's call this one puppy. And go down here and do puppy. So with puppy, I actually have the integral of 8 over x squared plus 2x plus 9. The substitution doesn't work. We just have a constant left over on top, but we can't force a substitution. This is a rational function, and it contains x squared plus 2x plus 9. So it contains a quadratic trinomial, which tells me that completing the square is a good plan. So we're going to complete the square here. So I have x squared plus 2x, and then I'm going to have plus 1 squared plus 9 minus 1 squared. And this gives me x plus 1 squared plus 8. So when I go and rewrite this integral now, I have 8 over x plus 1 squared plus 8 dx. And you might notice this is a known form. This is arctangent. And that x plus 1, it's not x squared, it's x plus 1 squared, but that's okay because the derivative of x plus 1 is 1, which is just a constant. So I could actually even think of this as 8, 1 over x plus 1 squared plus the square root of 8 squared. And I can see that my a is the square root of 8. So this is 8 times 1 over root 8, so 1 over a, arctan of x plus 1 over root 8 plus c. So puppy ended up not being that hard. Completing the square turned it immediately into a known form. So then we'll go back up here and write our answers. We have 1/2 ln of the absolute value of x squared plus 2x plus 9 plus 8 over root 8 arctan of x plus 1 over root 8 plus c. So now I'm going to go back up here. I took that away from this integral, that star, and just write my final answer. So my final answer would be the integral of that first one, which is a simple known form, plus what we got from star down there. So 1/2 ln of x squared plus 2x plus 9, plus we distribute that 1/2 to get 4 over root 8 arctan of x plus 1 over root 8 plus c. And that is my final answer to this partial fractions problem with that sort of intense integral that showed up at the end. So let's just take a second to think about that intense integral. Like I said, it shows up quite a bit at the end of partial fractions. So let's go down to the bottom here and think about what kind of integral it is. So if we have, actually I'll call this asterisk since I've already used quite a few stars. So if I have an integral that has a linear polynomial over a quadratic trinomial, we can always use this method, but especially if that quadratic trinomial does not factor. So even if it does factor, we can use this method, but the arctan that showed up won't show up. So hang on, let's write down our steps. So we're going to call this method forcing a substitution. And the first thing that we do when we're forcing a substitution is to let u equal to the denominator. And then we force the derivative in the numerator using the methods that we learned for special division. So in other words, multiply by 1, add 0, and separate. And then the last thing we do is apply the substitution to the first integral and complete the square for the second integral. So in other words, that first integral is going to give me a ln, and complete the square for the second integral. And if that quadratic polynomial does not factor, in other words, it is irreducible, then this completing the square will give us an arctan if irreducible. If, however, it could factor, you'll end up with the known form. That was the first question from assignment 4. So you'll end up with that known form, 1 over x squared minus a squared. And that was 1 over 2a ln of x minus a over x plus a plus c. And this is what's going to happen if reducible, so if it factors. So that's it. If it factors, a lot of times you're not going to end up at this step anyway, because you'll have done partial fractions. You'll have factored that polynomial in the partial fractions part. Okay, so we'll definitely be doing more problems like this. Like I said, this shows up quite a bit at the end of partial fractions, but hopefully that kind of gave you guys a little bit of a memory about how all of our integration techniques work. That's all. Bye.